In this paper, we present a novel method for intelligently resizing a wide range of volumetric data, including fluids. Fluid carving, which was built upon image-based seam carving methods, provided an exciting new way for artists and content creators to post-process and reuse fluid data. However, in its initial formulation, this technique was quite limited. It only supported particle-based flip liquids, and because it was built on image-based techniques, it inherited the assumption of rectangular boundaries. Furthermore, its graph-cut-based seam computations were slow in retargeting production-quality data. What if an artist needs to intelligently resize smoke or fire, and what if that data does not follow a rectangular path? These scenarios would be difficult or impossible using previous methods, but with our new approach, we eliminate each of these restrictions. We also provide a greedy seam computation method that is orders of magnitude faster than the previous approach, without sacrificing visual quality. I will now give a brief overview of our lattice-guided seam computation approach. Seams are traditionally required to flow monotonically from one rectangular boundary to the other. Therefore, this curved gray region cannot be resized using previous seam carving methods. Simply removing the monotonicity constraint leads to distortion and does not preserve shape silhouettes. Instead, we allow the user to enclose a region of interest in a non-uniform lattice structure and map it to a rectangular space where a seam can be computed in the usual manner. This mapping can then be used to apply seam carving to any shape that a user can create with our lattices. Like to this spinning smoke vortex, for example. Even on simulations that have a cyclic shape and motion like this example, our method allows post-process resizing that avoids distorting the most important regions as defined by the energy function. We visualize the seams in green as the vortex resizes. To enable fluid carving for volumetric simulations like smoke and fire, we present a new energy function that is based on vorticity and the gradient magnitude of any scalar fields that the volume has. Because our method is built around open VDB grids, the artist can easily craft and manipulate energy functions to their needs with a familiar system. To ensure that seams do not simply avoid the simulation altogether in this example, each component of energy is masked and weighted so that seams focus first on the flame, second on the smoke, and third on the empty region. Our method also supports animated lattices that track with the simulation, enabling scenarios like this wavy torch simulation. It also provides the flexibility to retarget complex paths that flow in multiple directions, such as this rocket smoke trail simulation. With our multi-greedy seam computation approach, which we describe in the paper, we maintain visual quality while computing seams in a fraction of the time of the previous method. This high-resolution smoke plume shows that we can support data that would be too large for the graph-cut method. Computing a seam on even a single frame of this simulation would take hours using the previous approach, while our method took little over a minute on the full 216 frames. We will now show a number of results with comparisons between the previous graph-cut approach and our new multi-greedy approach. Maintaining the round boundary of this chaotic bonfire simulation while retargeting would not be possible with the previous method. However, with our lattice-guided approach, the boundary shape tracks with the resized simulation without issues. This meandering river is a great use case for our method. By simply drawing a curve, the user can create a lattice which guides seams along the meandering shape. Notice that as the river resizes, seam pairs are used to simultaneously resize the riverbank, removing the need to manually modify the riverbank to match the retargeted river. In all of our results, the greedy seams were significantly faster while maintaining the same level of visual quality. In the paper, we also provide an analysis of an image dataset of 5,000 images to show quantitatively that carving the seams computed using our multi-greedy approach is very similar to carving the optimal seams computed using the slower previous methods. We also conducted a user study and found that our multi-greedy results were just as preferable as the graph-cut method. Our method also works great for retargeting regions within images. The combination of a lattice-guided approach with seam pair carving resizes the region of interest only, leaving the aspect ratio of the image untouched.